Artificial intelligence can now recognize images, write text, and understand human speech. With the emergence of generative AI, these capabilities have advanced dramatically. However, teaching AI to make decisions like humans remains one of the most difficult challenges. The reason is simple. Most AI systems learn patterns from data, but they do not learn the decision-making process that explains why a particular decision was made. This is where graph neural networks, or GNNs, have attracted significant attention in recent years. Unlike traditional AI, GNNs do not treat data as isolated points. Instead, they understand data as a network of relationships. So, what makes GNNs different from conventional AI? And can they truly move us closer to human-like decision-making? Let's begin by exploring the fundamental ideas behind graph neural networks. So, what exactly is a graph neural network, or GNN? Today, much of the progress in artificial intelligence has been driven by large language models, or LLMs. LLMs are exceptionally good at understanding language and generating knowledge. But the real world is not made of words alone. People are connected to people. Companies are connected to companies. And increasingly, AI systems are connected to one another. What GNNs learn is this very network of relationships. In a GNN, each entity is represented as a node, while the relationships between entities are represented as edges. Rather than analyzing isolated pieces of data, GNNs learn from the structure of the entire network. Because of this, GNNs are being applied in many domains where relationships matter, including social network analysis, recommendation systems, drug discovery, finance, and fraud detection. In other words, if LLMs are AI systems that understand language and knowledge, GNNs are AI systems that understand relationships and structure. But does understanding relationships alone enable AI to learn human-like decision-making? In fact, this is where one of today's biggest challenges in AI begins. Let's explore why. What do LLMs and GNNs have in common? From machine learning and deep learning to transformers and today's large language models, AI has advanced at an extraordinary pace. Yet beneath all of these technologies lies one fundamental principle. They all learn patterns from data. By processing larger amounts of data and discovering recurring structures and relationships, AI has become capable of recognition, prediction, and even generating natural language. In other words, although the models and training data have evolved dramatically, the core idea has remained the same. AI learns patterns. But is human decision-making really just a matter of recognizing patterns? In the real world, decisions are shaped not only by data, but also by goals, context, values, and relationships. And this is where today's AI still faces its greatest challenge. So, what has AI actually been learning all this time? A representative example is the large language model, or LLM. Despite its impressive capabilities, an LLM does not learn the meaning of language itself. Instead, it learns the probability of which word is most likely to come next by analyzing vast amounts of text. When generating a sentence, it builds the output one word at a time, selecting the most probable next word at each step. That is why LLMs can produce text that sounds so natural and fluent. In other words, the strength of an LLM lies not in understanding meaning itself, but in learning statistical patterns. But can human decision-making really be explained by probabilities alone? In reality, the world is far more complex. What we interact with is not just words. People connect with people. Organizations connect with organizations. Knowledge connects with knowledge. And all of these exist within the rules and institutions that shape our society. Countless relationships overlap and influence one another, giving rise to real-world events and human decision-making. In other words, understanding the world requires more than examining individual pieces of information. What truly matters is understanding how information is connected. It is these relationships that give information its meaning. So, how can AI represent such complex relationships? The answer is graphs. In a graph, each entity, whether it is a person, an organization, a place, a product, or a piece of knowledge, is represented as a node. The connections between them are represented as edges. The key is not the individual entities themselves. What matters is how they are connected and what kind of structure those connections create. By viewing the world as a graph, we can discover meanings and relationships that remain invisible when looking at individual pieces of information in isolation. and the AI that learns directly from these graph structures is called a graph neural network, or GNN. If a graph is a way of representing relationships in the world, then a graph neural network, or GNN, is an AI designed to learn from those graphs. Traditional AI typically learns from individual data points in isolation. GNNs, however, learn not only from the data itself, but also from the connections between them. Who is connected to whom? Which relationships are the strongest? And what kind of structure does the entire network form? By learning these patterns of relationships, GNNs can uncover hidden connections and even predict new ones. That is why they have achieved remarkable success in applications where relationships matter, such as social network recommendations, fraud detection, drug discovery, and knowledge graphs. In other words, GNNs do not simply learn from data, they learn from relationships themselves. But human decision-making is not determined by relationships alone. So, what else shapes our decisions? That is the question we will explore next. Now, let's pause and consider an important question. Graph neural networks are incredibly powerful at learning the structure of relationships. They can identify who is connected to whom. They can measure the strength of those connections. And they can learn the overall structure of an entire network. By learning these patterns, GNNs achieve impressive performance across a wide range of applications. But is that enough? For example, why does a particular relationship exist? What purpose does it serve? And what is really happening within that network? Humans do not look at relationships alone. We also understand the meaning, context, and purpose behind those relationships before making decisions. So the question is, can GNNs learn meaning as well as relationships? The answer is no. This is perhaps the most important point to understand about graph neural networks. GNNs are designed to learn relationships. They learn who is connected to whom. They learn how those connections are structured. And they learn how relationships propagate throughout a network. By learning these patterns of relationships, GNNs can make highly accurate predictions and recommendations. But relationships alone do not lead to meaning. When humans make decisions, we ask different kinds of questions. Why was this decision made? What goal was the decision intended to achieve? What criteria were used to choose one option over another? The answers to these questions cannot be inferred from the structure of relationships alone. In other words, learning relationships and learning human decision-making are fundamentally different problems. So, what do humans actually rely on when making decisions? Let's explore that mechanism next. When humans make decisions, the most important element is meaning. But meaning is not something that already exists within the data itself. Consider a single person. The same individual can be viewed as a patient, a customer, or an employee. Although the data remains exactly the same, its meaning changes completely. What creates that difference is the boundary, the way we define the world within which we interpret the data. This is what we call the boundary. Once a boundary is established, it determines the rules that govern that world. It also defines the ontology, the concepts and categories such as patient, product, or contract. Finally, humans make decisions by considering their goals, values, and the specific context of the situation. In other words, humans do not simply observe data. We assign meaning to the world through the framework of boundary, rule, ontology, and human, and then make decisions based on that meaning. That is why meaning does not exist inside the data itself. It emerges from how humans design and interpret the world. Now, let's consider a framework for recording human decision-making. Humans do not act based solely on the final decision. Everything begins with an event in the real world. From that event, we receive various signals and pieces of information. Based on those signals, we make a decision. However, even when different people observe the same information, they may reach different conclusions. The reason is that each person defines a different boundary and interprets the situation within a different conceptual world. Within that boundary, people assign meaning based on their goals, values, and experience before arriving at a final decision. The decision trace model captures not only the outcome of a decision, but the entire process that leads to it. In other words, it records what happened, what signals were received, how the decision was made, and under which boundary that decision took place. This complete chain of reasoning is what the decision trace model is designed to preserve. With the decision trace model, we can now record the entire decision-making process as a structured representation. But how can AI make use of these recorded decisions? The first step is to store every decision process in a decision ledger. Next, the relationships between those decisions are represented as a graph. This graph contains not only events and decisions, but also the boundaries and the meanings assigned by humans. The resulting structured graph is then learned by a graph neural network. Importantly, the GNN is not learning meaning itself. It is learning the relationships between decisions that have already been structured and given meaning by humans. As a result, the system can identify common patterns and meaningful differences across past decisions, enabling it to support decision-making in new situations. This is what we call the Decision Trace GNN. In other words, humans structure decision-making, and the GNN learns from that structure. By dividing the roles in this way, AI can continuously learn from human decisions and provide increasingly effective support for future decision-making. In this episode, we explored why AI still struggles to learn human decision-making. We examined this challenge through the perspectives of large language models, graph neural networks, and the decision trace model. What AI ultimately needs to learn is neither data alone nor relationships alone. It must learn how humans assign meaning to the world and how that meaning shapes their decisions. Capturing that process as a structured representation is the key, and that is exactly what the Decision Trace GNN is designed to achieve. In the next episode, we'll take a closer look at how the Decision Trace GNN actually works and how it learns from human decisions through concrete examples. Thank you for watching, and we look forward to seeing you in the next episode.